Hello and welcome to Professor B.S. Murthy, who is joining us here today for discussion on metallurgical and materials engineering. Professor Murthy is the head of our department of metallurgical and materials engineering here at IIT Madras. He's a highly decorated metallurgist, has won many national awards, including the Shanti Swarup Bhatnagar Award. And he is also the fellow of several national academies and also in many international organizations. So he is eminently qualified to discuss research and what happens in the research setting, what students undergo and what experiences they have in the materials domain. His areas of research include high entropy alloys, bulk metallic glasses and so on. So with these words of introductions, I welcome you to this interview. So, yeah, thanks. What would you think are traditional areas of materials science and engineering that students are likely to see?
Yeah, our department originally started in 1959 along with the IIT Madras as a department of metallurgy. So, basically looking at traditional metallurgy. When I say traditional metallurgy, our department particularly concentrated on what is called casting, forming, welding. These are the three core areas of our department. Not too much into the extractive metallurgy part of it, though there were a few experts in that area too, but that has not been a real strength of our department, particularly because there are not too many steel plants in and around Chennai. Okay, and that has been mostly the strength of places like IIT Kharagpur, which has been very close to so many steel plants. So, as a result, our department traditionally concentrated on, as I told, forming, metal forming, how materials deform, and then casting of them because there are quite a number of foundries in and around Chennai, and also what is called welding. Okay, there is, for example, a welding research institute in Trichy, which used to tie up with the IIT Madras Metallurgy department to a large extent. L&T used to have a lot of tie-ups. So, welding, which is a part of the manufacturing. So, if you can say the three major manufacturing processes, which are casting, welding and forming, have been the core of our department traditionally for many, many years.
Okay. So, I think maybe the general audience, including aspiring researchers, may not be fully aware. So, when you talk of traditional areas like welding, casting and forming, how relevant is research in these seemingly old areas relevant today?
Correct. For example, I take one example of welding. There is enormous research that is going on in welding on, for example, one of the major problems in typical traditional welding, which involves, let's say, you melt two pieces at the joint and then join them, and that can give you a lot of I would say weakness at the weld joint because of the melting and the casting that is involved during this solidification process. And there are a number of applications where you are not allowed for the joint to be exposed to very high temperatures. So, there is something called solid state welding that has come up in recent times. So, people are also working on friction welding, friction stir welding. So, where there is no chance of the two pieces, weld pieces being melted at all, and as a result in the solid state they join and they retain a number of properties of these materials, which is very essential for the component to perform in the application. So, as a result, solid state welding has taken up. Similarly, joining is no more a simple welding process. People are now joining polymers with metals, okay, polymers with ceramics, metals with ceramics. So, there is enormous research area in that. Okay. Similarly, now if I take forming as an area, there are new forming technologies that have come up. For example, hydroforming, sheet metal forming has taken up big strides in recent times for trying to get the whole. For example, if I take automotive car body, people want to have the whole car body made up of one single sheet instead of simply welding and joining a number of pieces. So, there are technologies that have come up where there is a lot of research has to go in to develop what is called stretchability inside the material, and there is a lot of physical metallurgy also goes in, how to develop such stretchability into metals, what kind of new type of alloys have to be developed to have a high stretchability. So, forming also including a new area what is called severe plastic deformation that has come in, where people want to generate ultra fine grain sizes inside the material by severely deforming these materials and use that for various applications in terms of enhancement of properties. So in each of these areas, there is a lot of work that is going on. For example, simple thing like casting. People are now developing what are called metal foams. Okay, which are very useful for, this is also a traditional casting process, excepting that you add some foaming agents to develop these foams, and there the whole technology of how to develop uniformly distributed cells is a big challenge, and there people are using newer technologies such as X-ray tomography to actually see the whole foam in 3D and try to design the foam in such a way that you get the proper properties. So in each of these areas, in fact, for example, people are looking at the casting as the solidification takes place. What kind of stresses are developed in the casting using neutron diffraction, and trying to see whether I can do something to suppress what is called hot tearing. Hot tearing is a major problem in engine blocks and pistons and things like that. When people are developing, there are problems that people encounter during the solidification because of the stresses that are developed. So people are using modern techniques to study them and trying to identify how do I control it.
Okay, so I mean the terms for these technologies, for these areas of research may look traditional and ancient, but really there's a lot of modern activity that goes on and a lot of challenges in these.
A lot of challenges in each of these areas.
Okay. So, of course, materials is a very large field, and then virtually every field of engineering has materials in it. In recent times, what has been new areas that people have focused on, interesting areas that have come up recently that large groups are working on?
Yes. Okay. As you rightly said, I always tell people materials is the backbone of everything. Without materials, you cannot have anything. In fact, I say everything in this world is either spiritual or material. So, to that extent, materials are that important. And when we say, as I was telling you, we started the journey in our department as a traditional metallurgy, and then around 2003 we realized that the non-metallic materials are also equally important, not only the metals. So we introduced ceramics, polymers, composites, everything into our curriculum. In fact, we even changed the name of the department in 2003 to Department of Metallurgical Materials Engineering, which is what now the department is named after. So in that connection, a lot of newer areas, for example, electronic materials, polymers, composites. When I say composite, it could be polymer matrix composites, metal matrix composites, ceramic matrix composites, ceramics, high temperature ceramics. So if I now look at the composition of my department, half of the department faculty members work on non-metallic materials areas, and as a result, materials such as biomaterials, nanomaterials, okay, variety of nanomaterials including carbon nanotubes, which you yourself work on, and materials which are for extremely high temperature environments. For example, something like nose cones of a missile. Okay, so you need materials which can withstand extremely high temperatures. Similarly, various coatings for high temperature applications people are developing. You just mentioned about high entropy alloys. People are trying to develop them as coating materials on superalloys, so that it gives additional high temperature capabilities for superalloys. Like this, a number of new areas. For example, electronic materials, quite a number of people in our department are working on that. So, optoelectronic materials, for example, thin films, semiconducting materials, and magnetic materials. So, you name every material, now we have people working on these things, and they have really taken almost equal importance to traditional metallurgy areas. That if I look at the composition of the department, it's more or less balanced in terms of modern materials and the traditional metallurgy.
Okay, very nice. So that gives us also an overview of what sort of industries are looking for these kinds of things, and where people may be able to take their experience here to some setting where these kinds of things are necessary. So, of course, you are yourselves a very successful researcher, a very well decorated researcher, and so on. And there are many, if you look at, you do some general reading, there are a lot of criteria people use to say that so and so has done well in research and so on. But setting aside numbers, in your view, in what way would you measure success in research?
Yeah, I would say anyone who can make an impact on either an industry or the future researchers is what I would consider it as a success. That the work that you have been doing, has it been really bringing newer technologies, newer process, newer materials which an industry is able to use and make itself as a leading industry in the global arena, is one way of looking at success. Or the other way is your research has kind of nucleated a number of other researchers, okay, which people have taken up a cue from your research and started working on that and taking it forward. This is another way of looking at it. Okay. So basically it all depends on what kind of an impact that you are making either on the industry or on the research.
Okay.
Of course, people use numbers as a way of looking at it, but not always numbers are important. Among the numbers, which are the ones which have made more impact on the society? Of course, it's also important when we talk about in this context, has it also made an impact on the general development of the country in terms of the societal needs? Okay. Needs, yes. So that's also very important. Okay. Rural development areas, there are a number of newer materials that are being developed which are being used for certain applications in even agriculture, so that we grow better. So these are all the things which are, I would say, the matrix people should use
to gauge how well,
in my view.
Okay, very nice. So if we step back and we have new students who are coming from various backgrounds and who join research programs in various institutions across the country, they are moving away from college education, undergraduate education to postgraduate education and so on. In your view, what are the typical kinds of challenges such students face, especially let's say coming into a materials kind of a department? Correct.
The basic difference between an undergraduate education where you are kind of coached, okay, to study some material or certain reading material, and then you go through certain exams and then get certain grades out of it, to research is the basic difference comes is the where you try to independently do most of the things yourself. So PhD is a training ground where we train people how to plan a certain work and execute it, analyze what comes out of it, and then bring out some logical conclusions out of it. All these things has to be inculcated in a particular student, which most of the students who come from the undergraduate education are not really trained on that. And also particularly materials research needs handling a number of instruments. Of course, there is a lot of computational research that also goes on in materials. For example, the new buzzword now is called ICME. Integrated computational materials engineering, people call it as starting from the atomic level to the macro level. Can we connect everything? What people call it as multi-scale modeling. So there are people who are trying to do that. There also many people might have learned software as a software per se, but not utilizing the software for solving certain problems, real life problems. That poses a lot of challenge when a student actually comes into research. This is one aspect. Second aspect is in the experimental work where handling various equipment. Okay, for example, making materials itself is a major challenge, and that has to be made in certain conditions so that there is a reproducibility that is essential in any scientific research. So that is another thing that has to be trained by the faculty and the senior students to the newly joined student, and also handling various characterizing facilities. Just by making a material, as simple as I can tell you, anybody can easily make a nanomaterial nowadays. But to prove to somebody that you have made a nanomaterial is not so easy. It needs various microscopes which are extremely expensive. Starting from anywhere ranging from about 1 crore, it can go up to almost like about 17 crores. We recently have bought a microscope in our institute which costed us almost like 17 crores, where it can go up to 1 angstrom resolution. So you would like to see these materials at that level, and that needs a lot of training. So we have a number of these training programs. For example, we have a course which is called Practical Transmission Electron Microscopy course, where one full semester the student goes through how to handle such a sophisticated instrument, starting from how to prepare a sample for that instrument to the last day where he will demonstrate a good microstructure from such a microscope to be able to make himself eligible to handle such kind of sophisticated instruments. All these need to be trained. So that's why the whole 3 or 4 or 5 years, the time that the student spends here for either an MS program or a PhD program is basically towards this kind of a training. So these are the challenges. Of course, they look as challenges when you start with, but there is a lot of enjoyment in learning all these things.
Lot of opportunity.
Lot of opportunity, lot of enjoyment when you do it, and when you learn many of these new techniques, they are going to be of a great use when you go for a postdoctoral research later, where you are supposed to do independent research, and then also when you yourself become a faculty member to guide the next generation students. All this training will be of a great use.
In fact, yes, along those lines. So, what sort of positions do you typically see postgraduate students, people completing MS and PhD from our department? What sort of positions do you typically see them going towards?
Typically, the majority of the positions, I would say, are academic positions, faculty members in various. Now, in fact, that opportunity has significantly grown. If you look at it, once upon a time there were just 5 IITs. Now there are almost more than 20 IITs. Possibly a number of 23 or so. I do not exactly know the correct number, but something around that. Yes. Okay, and then NITs. You have about 1 NIT for each state. I heard that there are about 30 NITs and a number of private, academic institutions which are also of a reasonably good standard are coming up. In fact, some of them are taking up faculty who are being called as research faculty. They don't need to even teach. They simply, their job is to keep on doing research, get projects, publish papers, so that their visibility in the research arena is grown. So this is one spectrum which has grown to a big level, that the opportunities for PhD students into those has significantly grown. This is one. Second is, earlier the industry never used to really take a number of PhD students. Okay, they say, a BTech is good enough for us. But it is now, you see, quite a number of industries are taking research scholars, I mean people with an MS or PhD background, particularly because they would like to compete globally and become global leaders. For example, in Chennai itself, if you look at it, Mahindra & Mahindra has set up a big R&D center where they are looking for people with a research background. Similarly, a number of multinational R&D institutions have come up. For example, GE has their own setup in Bangalore, who are taking a large number of materials, people with materials background with MS or PhD, including even Tata Steel every year is taking a number of people with a PhD background, so for their own R&D. So the industrial R&D is picking up in a big way. Thanks to what we call it as Make in India now. Okay, with that movement, a lot of industries are trying to make their products globally competitive, and not only globally competitive, they would like to be global leaders. Okay. So that is where research is very crucial, and people with research background are able to fit themselves into such an environment and then grow much better.
Okay, very nice. Now, supposing we step back a bit and look at the time that postgraduate student spends here as a researcher through his degree program. A very mundane question: how often should such a student meet his advisor, his or her advisor?
There cannot be a prescription for such a thing. Sure. Okay, it depends on the student. Okay, how capable he is to handle things on his own. It depends on the background the student comes from. And depends on the problem that he is tackling.
Okay, fine.
If it is a very difficult problem, I would even suggest, but it also depends on whether you are in the beginning of your research or are you moving towards the fag end of your research PhD degree or so. So initially it is suggested that you meet almost on a weekly basis, okay, so that you are sure that you are on the right track. And once you feel, yes, you got a hold on the thing, that things are moving well, and then possibly, I would suggest at least once in a month, if not more frequently than that. Okay. I usually meet my students once in a fortnight. Okay. So once in a fortnight, about an hour I spend with each of my students, and I tell them that if you have any other issues, okay, you are free to come and meet me anytime. But I would suggest that initial days it is more important to meet more frequently, because the student is not used to first of all planning things. In any research, if you don't plan anything properly, ultimately the result is not going to be as expected.
Okay.
So as a result, during the planning stage, it is very essential that you are in touch with your guide more frequently, because his guidance becomes very useful in that initial period. Later, you are possibly able to guide yourself on your own.
Okay. So, I would like to close with this question for you. What would your advice be to an aspiring student in metallurgical and materials engineering?
Okay. For that matter, any area, if you are doing PhD, whether it is metallurgy or not, you should first enjoy. This is very important. Okay. I would always tell this, for a research scholar, you need to have 3 qualities. Okay. You should be able to go for a cup of coffee with your friends and discuss research, not a cricket match that has happened possibly the previous day or so. And then you should be able to go to bed thinking about the problem that you are trying to solve. Okay, that basically means you are involved in your research. You do not take research as one of the activities that you do on a daily basis, but it is the activity for you, the most important activity. Most importantly, I would say the third one is you should be able to catch an youngster, okay, just joined in your group or possibly a 12th standard kid, and make him excited about what you do. What is very important in research is to be able to feel that you are possibly the first one to be working in that field. After all, any research, if you simply repeat what somebody else has done, you would not get a degree. So every PhD student, wherever he is working on a problem which possibly nobody else is working on. At least a particular facet of a problem which he is uniquely trying to develop a solution for that. So he should feel excited that he is the only one who is working on that. And that excitement in research is very essential. If you don't retain that excitement and that fire in you, obviously research is not enjoyable. And if you don't enjoy research, there is no point in doing research.
Okay, so involvement and enjoyment.
That's very essential.
Thank you so much for joining us.
Thank you.
Very useful.
Thank you.